Roller coasters have been a source of entertainment for a very long time, but have you ever stopped to wonder why it is that riders are able to stay put in them no matter what direction or speed they go? And no, the answer isn't as simple as seatbelts. It has everything to do with physics. Take a bucket of water, for example. We see that no matter how many times it goes upside down, it stays put in a bucket. But how? And why?
This is a diagram of a roller coaster going in a loop simulated by the bucket. When moving in a circle, there must be a net force directed toward the center of the circle in order to provide the centripetal acceleration, which we will analyze shortly. The force diagrams, when the bucket is at the top, has the normal force and the weight directed down, meaning that the net force is directed towards downwards, towards the center. Here at the bottom of the circle, the normal force is directed up and the weight force is directed down, making the net force directed up. From here, we can establish a relationship using Newton's second law of the net force. So you find the x and y components. So here we would just be using the x component, and you write a relationship, and you can rearrange to get the equation normal force is equal to m times v squared over r minus w. So normal force is equal to mass times velocity squared over the radius minus the weight. As velocity decreases, there comes a point where mv over r is going to equal w, and n will be equal to 0.
Here we can see that the arm is moving at a constant speed. We can clearly see that the bucket is in fact going upside down, but no water is spilling out. Now, what would happen if her arm or the coaster was going too slow? The term critical velocity is used to figure out exactly how slow the bucket could turn without the water falling out, like we'll see here. This was obtained by square root g times r, where g is free fall and r is the radius. This was obtained using the relationship found from Newton's second law. The formula was rearranged to get velocity by itself. This value is the slowest speed at which the bucket can complete a circle without the water falling out. The critical velocity was then compared to our data from the experiment.
The critical velocity was calculated to be 2.97 meters per second, which is the slowest speed that the bucket can complete a circle without the water falling out of the bucket. And then our velocities were calculated from 3 different periods. And then they were compared to the critical velocity. So if it is greater than the critical velocity, it will stay in the bucket. But if it is lower than the critical velocity, the water will fall out.
So then how fast should the bucket go for the water to stay in it, like we see here?
The centripetal acceleration was also determined from the same 3 periods as seen here. And if the acceleration was less than the free fall acceleration, it will fall out of the bucket, but if it is greater, it will stay in the bucket.
It is concluded that an acceleration greater than free fall keeps the water in the bucket, but an acceleration less than free fall causes the water to spill out. So this is why roller coasters must stay a certain speed in order to keep passengers safely inside. Well, now we know how they work. Thanks for watching.